This method has a big advantage. No need to install acceleration sensors on your vehicle. Now the SPEEDO code is finally here and I will explain it. This project is based on precise time measurements using optical sensors and some computation the ESP32 processor is doing for us. The measuring method is accurate and universally applicable. We designed a 3D printed housing for our SPEEDO project, which we will share on PCBWay's community platform. However, there are many more reasons to visit PCBWay's website. No matter whether you are a professional or you want to realize a DIY project, you will find suitable PCB products and manufacturing services. Take the easy way with PCBWay. Our method using optical sensors has great potential for a number of projects. We were showing the principle, the mathematics, the accuracy and a number of tests in previous videos. Peter is using it to measure acceleration and takeoff speed on a launch catapult for model airplanes. He added a nice graphical user interface and extended our code to measure more parameters. A great project. Thank you very much, Peter, for the material. After Espressif changed the syntax for some functions as part of the 2.x to 3.0 migration, we had to adapt our code accordingly. You're invited to watch our video about it. Instead of IR proximity sensors, you can use light barriers or other sensors. They only need to be fast. It is extremely important to use an interrupt routine for time measurement because it's taking priority over other processor tasks. Actually, this part of the code caused most of the development effort. You wouldn't expect it at a first glance. Here is the definition of variables applied within the interrupt routine. We need to distinguish between left and right movement. I will explain why in a minute. The microsecond timer is counting up continuously. As soon as a vehicle is detected, query conditions are becoming true, and then the variables T3, T2, T1 and T0 are set to the timer value. Since real objects are often causing multiple triggers, we need to block all queries after the first detection and release it later for new measurements. Furthermore, false triggers may occur due to unwanted reflections, causing incorrect measurements. We are avoiding that by checking the logical sequence, which is quite an effort, as you can see. We had to define a minimum measurable speed to avoid the SPEEDO waiting forever for the next sensor trigger after a first one. This query is resetting the measurement after a time interval corresponding to the minimum speed. Next, we are assigning the measured timer values to global variables that we are processing outside the interrupt routine. Theoretically, the method works for both movement directions. However, in practice we can realize more resilient measurements having a separate procedure for each direction. If the movement is not left but right, then the second part of the routine comes into play, where we are processing all signals reverse. From the timer values measured, we are calculating the time intervals for the vehicle to cover the distance between the sensors. Then we are computing the acceleration and the speeds using the method that we derived and tested in earlier videos. This subroutine is discovering and indicating an invalid result in case a trigger signal is missing. The main loop is containing the subroutines mentioned, in addition to a number of subroutines for control and presentation of the results. We implemented 8 LED features that you can take or leave. The first blue LED is indicating the status of the Bluetooth connection. It's flashing while searching and it's lighting up constantly once the connection is established. The second blue LED is flashing while an object is detected. The two white LEDs are indicating the direction of movement, which can be changed. At the moment I'm sending the corresponding control commands via a terminal program. The green LED indicates a valid measurement, the red LED an invalid one. Our code is pretty robust. As you can see, I can hardly provoke an invalid measurement. In a series of measurements, the maximum speed and acceleration values are stored. Whenever the acceleration maximum is topped, the red LED starts this flashing sequence. The yellow LED is flashing accordingly when the speed maximum is topped. In addition, all new top values are sent via the serial interface. There is a number of subroutines to communicate via USB and serial Bluetooth. We can even request different report levels, which we called light, medium and full. Simple string commands are used for configuration and control. You saw all these in action in earlier videos. The Bluetooth connection is based on a standard library, and here is the name to find the device in the settings of your PC or smartphone. Sending Y during pairing is automatically establishing a secure connection. In the setup, we are defining certain variables to store configuration data permanently. Next, we are defining the output pins for the LEDs and the input pins for the sensors. The following is defining our interrupts triggered on the falling edge of our sensor output signal. The remaining stuff is standard for the serial USB and Bluetooth interface. We explained everything: the principle, the MUD, the 3D printed housing, and finally the important parts of the code. The method is universal. You can measure from very slow up to pretty high speed. Just write your application ideas in the comments. The download link for the code and more is under the video. Have fun building it. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.